Organic chemistry again. Today we're going to think about why stereochemistry matters and where it will be important. So, let's take this molecule as an example. This is ibuprofen, invented in Nottingham, and it has a stereocenter. Let's see if we can identify it. This carbon has two methyl groups, so it can't be a stereocenter. This carbon has two hydrogens, so it can't be a stereocenter. Two of the groups are the same. These are all in a ring. This carbon is flat. It's an sp2 hybridized carbon, so it doesn't have two forms, so it should be this one. This carbon here has this acid group on one end. COOH is an acid. It has all of this shit on the other end. It has a methyl group pointing up to the top. That's what this line represents, because it's a carbon. And the other bond, not drawn on this particular model, is a hydrogen. Therefore it has four different groups. That makes it an optically active center. So why does that matter? Well, it turns out that only one of the two possible optical isomers, only one of them, has the effect that we would expect, the ibuprofen effect, painkilling effect, and the other one does pretty much nothing. That means 50% of all of the drug that the company makes is completely wasted. It does nothing, and then it gets shipped, so all of that is weight. Then it gets eaten or not, so they also have disposal, and then if somebody eats it, they pee it out, and that has to get dealt with by sewage systems, and including a chemical that has no noticeable effect, and it may have some negative effects. In this case, there are no known negative effects. This is just one center where 50% of it does nothing, but if we imagine it had another optical center here and only one of the possibilities worked, then 3/4 of it, because if there are two centers, there are four different molecules that are possible. 3/4 of the chemical would do nothing at all, and obviously the waste goes up exponentially and extremely fast if we have more and more optical centers in our molecule. And so we're motivated to investigate optical isomers and to try to make pure isomers of one sort, because biology cares. If biology didn't care, it wouldn't matter so much, but most of our organic chemistry goes into interacting with biology. It's drugs, poisons, herbicides, treatments for all kinds of things. The other common molecule that we might think about is this. It's lactic acid, and again it has one optical center. In this case it's the only carbon it can be, so this carbon has three hydrogens, so it's not that one. This carbon is flat, so it's not that one, so it must be this one. It's got a hydroxide group, a methyl group, and this acid group on it, so it's chiral. One form of lactic acid is common in biology, and the other form is very rare. That means that we can generate things. So from our biomaterials point of view, we can generate polymers, where if we use the form that's common in nature, it is biodegraded very quickly, and if we use the form that is rare in nature, it's biodegraded very slowly. Chirality was discovered, however, on this molecule, tartaric acid, by Louis Pasteur, the famous Louis Pasteur of pasteurization. But in this case, he was interested in this molecule, a byproduct of wine production, and it has two chiral centers, but it is also symmetrical, and that means that it's got less possibilities. So normally if we had two chiral centers there would be four possibilities, but because it's symmetrical along this axis, there are only two possibilities. Either these two hydroxides here are on the same side of the molecule, or they're on opposite sides of the molecule. So if we have one up, one down, that is different to if we have them both on the same side. What Pasteur discovered was that there are two forms, and if you crystallize this, it forms two types of crystals that, if you're patient, you can pick out because they are mirror images of each other. If you feed it to microorganisms, they prefer one form to the other. But when it's produced in wine, it forms both of them. That makes an easy way for making a much more pure form of one of the two enantiomers, one of the two types of this molecule, and therefore you can investigate it more. So that brings us to our main theme of today, which is two reactions known as SN1 and SN2. So if we take this, the subscript is N for nucleophilic, which we will explain in a moment. The S means substitution, which is a type of reaction or set of reactions where one functional group, one chemical, is replaced by another, substituted, and the number is the order of the reaction. So in an SN1 reaction there is only one reagent that is taking part in the most important step, which is the slowest one. And in the SN2 reaction there are two reagents. Everybody does SN2 reactions first, and I can't think of a way of doing it better, so I'm going to also do SN2 reactions first, although number 2 you would think they come second. It's because the line of logic of explaining it works better this way around. So if we take this reaction, we are substituting the chlorine on this chloromethane, CH3Cl, for a hydroxide group, creating methanol, creating methanol, and we ought to also write in the chlorine has to leave somehow as a chloride ion, because we obviously can't generate or destroy charge. So what has this got to do with the topic at hand? Well, we're interested in how this happens, because we want to generate things that have a certain orientation, have a certain optical orientation. But if we investigate this reaction, we can vary the concentration of the reagent, so we can have more methyl chloride, and we can have more hydroxide. We can change the pH effectively, and we can see how that has an effect on the rate of the reaction. In this case, if we double the amount, the concentration of methyl chloride, the reaction rate doubles. And if we double the rate, the concentration of hydroxide ions, then the rate also doubles. That means that this is a second order reaction, which you will talk about in physical chemistry, measuring the order of reactions. So now I've redrawn the molecule with tiny h's for the hydrogens to emphasize the bonding orbital, which is here, which is where the electrons are hanging out between the chlorine and the carbon, which is not labeled, it's at the corner, and the anti-bonding orbital, which is where no electrons are hanging out at the moment, but if we want to break this bond, we would have to shove some electrons in there. We either have to take the electrons out of the bond to break it, or we have to put electrons into the antibond. Either of those things will kill this bond. So now we've also got the hydroxide ion, which has two lone pairs. This one is the one that's going to do the work because of the way that I've drawn it. This one's out of the plane. This is our lone pair that's going to do the attacking, and it could either attack here into the antibond, but then it would be connected to the chlorine and it would make a broken part of the molecule. It's a possibility. We will have a look and see why that isn't in a moment. And here we could attack it into this carbon, into the antibond here, but we would have to come from the back between these hydrogens. So where is it going to attack? It can attack at this chlorine, but the chlorine has a high electronegativity, so it's got a slight negative charge and it will repel the electrons from the oxygen here. The carbon, on the other hand, has a slight positive charge, so the chlorine has got a slightly larger proportion of these two electrons in the bond. They're sitting here, not quite in the middle, and that allows this part to be more attractive for these two electrons here to feed into here. So if we make our molecule optically active now by labeling these 1, 2 and 3, they're not hydrogens now, they're all different things, but it is still possible to do this reaction. That happens in some cases. It could be a methyl group, an ethyl group and a hydrogen. We can then attack the center with our hydroxide, And what we will see is the new bond to our new O is the other way round. So let's rationalize that now. So now what we see is the hydroxide comes in, flips these three groups over to the other side, the chloride leaves, giving us this compound here, which I have rotated in the plane of the board to here. So that brings the 1 down to the bottom and this leaves the 3 and the 2 as they were. And then if I rotate this bond so that we can get it closer to here we are where we started, to get the 1 to the top, then we can see that it is the opposite enantiomer as we started from. Obviously because we flipped 3 of the groups round to the other side and we forced it by attacking into the antibonding orbital, we forced it to keep its geometry, but it's flipped over to the other side. I like to imagine this as like an umbrella. If you have an umbrella in the wind, it can flip inside out. Now if we look at a different molecule, this one, tertiary butyl chloride, where those hydrogens are swapped for methyl groups, it is very difficult for any group to come along from this side because there's just too much stuff in the way. All these hydrogens in here make it very tight inside the back here. That is the speciality of the tertiary butyl group. It has a very good propensity for getting in the way, or very bad if we don't want it. So if we take this chemical and try to do the same reaction, it doesn't do the same thing. However, if we do the reaction and get it to work, if we get the conditions right, we can make the tertiary butyl alcohol in the same way, but the mechanism is different, which we can see if we make our compound optically active. Or we can see if we vary the concentration. So if we do this and vary the concentration of hydroxide ion, what we see to our surprise, if we're used to SN2 reactions, is that the concentration of hydroxide has very little effect on the rate of the reaction. Obviously, if there's no hydroxide in there, the reaction can't go, but over a very wide range, the concentration of hydroxide has no effect on the rate at all. It is only dependent on the concentration of the starting material. It's a first order reaction, only dependent on one thing. If we imagine this reaction takes place in 2 steps, where the chloride first of all leaves, leaving a positive carbon, and then the hydroxide attacks, then we can rationalize what's going on, because in the slow reaction, that determines how fast our process appears to be, because if this is very fast comparatively, it won't make a lot of difference what the concentration of hydroxide is. If the slow reaction only involves this component, that works. But what does it do if we choose an optically active starting material? So we can see if we label them 1, 2 and 3 just like we did before, but don't define what they are, we can see the same thing happens. We can follow where they go to, but we get to this step and we have to look at what the orbital structure of this is to see what shape it is. So if we look at this, we can imagine that these are 3 bonds that are repelling each other as far as they can, or we can look at the orbital structure and see that there are 3 sp2 hybridized orbitals, and there's a p orbital left over which has no electrons in it. That makes it flat, this intermediate, and it means that this chloride can either attack into this side or this side, giving us 2 possible products that are optical isomers of each other. So if we start with this molecule as a pure single optical isomer, we will get this molecule, but we will get both optical isomers out of this reaction. Whereas if we do the SN2 reaction, we will get the opposite optical isomer of the one that we started with. So now we have 2 reactions that do the two of the possible things that we could have. If we have a chiral center, if we have a chiral center, we could either keep it as it is, we could flip it the other way round, or we could lose whichever symmetry it has, so it could become completely mixed. So if we draw both of these reactions on an energy scheme, this on the bottom is called reaction coordinate, the progress of the reaction. So it's not really it's not a very easy axis to imagine, but if we imagine the progress of the reaction, we can see that we start with our starting material. The other compound comes along, that was an OH minus, which we call a nucleophile because it attacks nuclei. It's a negatively charged species that likes positive charge, so it attacks the nucleus. The nucleophile comes along, that in this case is B. It comes along and it forms a species, but because this has 5 bonds to carbon, it's not a real chemical that we can stop at. This is a high point of our reaction. That's the hardest thing to do in this case, and then it falls back down to the product. I've put the product at a lower energy, but it doesn't have to be a lower energy. If we look on this side, our SN1 reaction, which I haven't labeled, we go up past the energy barrier. That's the highest thing, the hardest thing to do. It forms a carbocation, the positive carbon, over here, which is flat, a positive carbon molecule, and then it goes back down in energy to the product. The interesting thing about this is we cannot measure. We can't stop at this point. We can tell that it's done it, but we can't stop at this point. This compound you can measure in solution, and if you cool the reaction down very quickly, it is sometimes possible to actually catch it. Obviously, this is incredibly reactive, so it's not possible to just have a bottle of it, but you can detect it, you can measure it by spectroscopy. We know that it's there. If we have 2 mechanisms for the same reaction, we should think about which conditions we can use to make it do one thing or the other. So the first thing that we've considered is if things are in the way, the tertiary butyl group, if there are lots of carbons and hydrogens or other atoms in the way at the back of the molecule, it is very difficult to do an SN2 reaction. The other thing we can vary is the energy of the intermediate state. That would be the carbocation. So this is our carbocation, and anything that makes this more stable will make it more likely to be able to be formed. That will reduce the energy required to make it, and so that would make an SN1 reaction more probable. How can we make this more stable? We could push in charge from whatever we have on the outside. If we can't change the chemicals that we start with, we could also help charge from the outside. That means that this reaction is more likely in a polar solvent. So if we take water as the solvent, the water will stick, the oxygen of the water, the lone pair on the oxygen of the water will stick to this positive charge and make the energy, the activation energy, lower. If we do the same reaction in a non-polar solvent, such as benzene for example, it will be a whole lot less likely and more difficult to form, and it will tend to drive the reaction to go by the SN2 pathway. If we look at the things on the outside of this, if this is a methyl group, it can interact in 2 ways. If we have a methyl group on here with a carbon-hydrogen bond, the electron density from this bond can interact with this positive charge and reduce the energy. It does that by spreading the positive charge more effectively around the molecule. The methyl group in itself is slightly electron donating anyway, so it will be pushing electron density. It will be making this carbon in the middle slightly more negative than it would otherwise be. So if we have 3 methyl groups on there, it is much more likely to be able to form the carbocation than if we do the opposite. Let's try it the opposite way around. So if we put 3 chlorines on there and have tetrachloromethane, for example, and we want to form this carbocation from it by taking away one of the chlorines, that is comparatively difficult because these chlorines are electronegative and they are pulling the electrons away from the carbon in the middle, making it positive to start with, and we're now trying to make it even more positive, which is obviously difficult. So to summarize, optical isomers are important because biology cares. Biology usually uses one type of optical isomer of the same compound and ignores the other one completely. However, sometimes the other one will have a different biological effect, so that would be even worse. That means that there is a pressure in chemistry to be able to make pure optical isomers of just one sort, so make the chemical but not make a mixture. That led us on to the SN1 reaction, which is a particularly poor example because it causes us to lose any optical purity that we had. So if we start with pure natural lactic acid of just one form and we react it using an SN1 mechanism, we get both products. It might be our goal. We might want to separate the other one, the one that's harder to get to. But obviously, half of our material will be completely wasted. And the fact that we started off with an optically pure material, which is usually more expensive, is also completely wasted. The SN2 reaction, on the other hand, conserves the optical purity of the product. However, it flips our center through the carbon atom, usually making it the opposite form than it was before. Although when we formally name these things, which we'll do next time, or you will have done in exercises, you'll see that that doesn't always tally. However, we are pushing the groups round to the other side of the molecule, and the thing that we've added is on the other side of the one that we've taken off. So the substitution also involves an inversion of the stereocenter. See you next time.